In section 4.4, we talk about another way to take two sets and form another set. The difference with these is we're going to create a set that contains elements that are completely different in nature from the original sets. In other words, we're going to take two sets, A and B, and we're going to form ordered pairs out of elements of A and B. To do this, we create what's called an ordered pair, which is probably a phrase you've seen before, where X comes from A and Y comes from B. We'll give the formal definition in a moment, but it's really important to emphasize the fact that these are actually ordered pairs. Okay? In other words, A comma B is not equal to B comma A unless A is equal to B. This is an important thing to keep in mind as we progress later on to the notion of relations. And in general, two ordered pairs are going to be the same if and only if the first coordinates are equal to each other and the second coordinates are equal to each other. With that idea in mind, let's look at the formal definition. So we say that the Cartesian product of A and B is the set A cross B. We say it A cross B. A cross B is the set of ordered pairs AB such that A is an element of A and B is an element of B. This is not the same as the intersection definition, because notice we're talking about taking elements from two different sets. And again, these are ordered pairs, so it's really important to make sure we enclose the ordered pairs in parentheses. They're not subsets, because remember, subsets, the order of the elements in the subset doesn't make a difference. But ordered pairs, it does make a difference, and that's what we're focusing on for right now. As an example, let's look at two finite sets with names of people in them. We have set A, which is John, Jim, Dave. Set B, which is Mary, Lucy. What is A cross B and what is B cross A? A cross B is the set of ordered pairs where we take one element from A and one element from B. One element from A, one element from B. One element from A, one element of B, and so on. So what you should try to notice is that they're doing this in a systematic way to make sure that we get all of the possibilities. We could just randomly grab one from A, one from B, and make some ordered pairs, but if we don't do it in a systematic way, it'll be really hard to make sure that we've got all of them. Kind of like when you're making a truth table and you're trying to decide how should I arrange the T's and the F's in the truth table so that I make sure I get all the possibilities for the given number of propositional variables I have. Let's look at B cross A. Remember, these are ordered pairs, so B cross A means I take something from B, comma, something from A. The elements of B cross A in this example would be Mary, John, Mary, Jim, Mary, Dave. Notice there's a systematic way of doing this. Once you've exhausted all of the possibilities that start with Mary, then you start with the possibilities that begin with Lucy, that have Lucy as the first coordinate. So we have Lucy, John, Lucy, Jim, Lucy, Dave. It's important to notice that none of the ordered pairs in A cross B or B cross A, nothing from A cross B or B cross A is the same. There's no elements of this set that are the same. Again, I'm going to emphasize that an element of a set of the form A cross B is going to be some sort of ordered pair. Okay? So A cross B as a set in general is not going to be equal to B cross A. So I say in general because there are instances where they are actually equal to each other. But in general, no. Consider one more example. Let's figure out A cross B and A cross A. If A is the set 1, 2, B is the set 2, 5, 6. So take a moment to look at the ordered pairs. Notice the systematic way in which they were written so that all the possibilities would be accounted for. For A cross A, notice we're taking one element from A and another element from A. And we're doing that in all possible ways that we can until we've exhausted all the possibilities. For part B of this example, our set A is a singleton set. It's just the set consisting of 5, and B is the set 0, 7. So take a look at these answers and make sense of them for yourself. Now you're going to go ahead and try a hands-on exercise on your own. So take a moment to pause the video and try this hands-on exercise for yourself. Now we're going to consider how do you describe Cartesian products between sets that are not necessarily all finite. We'll explore that through example 4.4.4. We're going to look at the Cartesian product of the interval 1, 3 cross the set 2, 4. Notice the interval 1, 3 has all real numbers between 1 and 3. There's infinitely many numbers in this interval. Any decimal number you could imagine that lies between 1 and 3, including 1 and 3, since the brackets are square, that will be in this set. The second set in our Cartesian product is just a finite set consisting of the two elements 2 and 4. Because one of our sets in our Cartesian product is infinite, we can't possibly write all the ordered pairs. We're going to use set builder notation. Now, for set builder notation, we have to make sure we write ordered pairs as the form of the elements in this set. Because remember, Cartesian products elements are always ordered pairs. So the way we would describe 1, 3, the interval 1, 3 cross the set 2, 4 is the set of xy, set of ordered pairs xy, such that 1 is less than or equal to x, which is less than or equal to 3, and y is equal to 2 or 4. Another way to do it, since the second set is finite, is you could say it's the set of x comma 2 and x comma 4 such that 1 is less than or equal to x, which is less than or equal to 3. Now you're going to try this hands-on exercise. Notice the subtle differences in notation as you try to use set builder notation the way we did in this example to express the Cartesian product of these two intervals. Try that before you watch the next video in the series.